these two. Okay, so in this joint work with Giuseppe de Giacomo and Aniello Murano, we extend strategy logic to show how we can talk about refinement of strategies. And we also introduce non-deterministic strategies because otherwise it doesn't make so much sense talking about refinement of strategies. So just 1 second. Okay. So first, what is the main area in which strategy logic comes into play? It's mostly in program synthesis. And so the purpose is to synthesize programs of a certain kind that interact with an environment or with other components of a system, and that may run forever. For instance, classic examples are operating systems or controllers in power plants. And a very classic language to specify the properties that the programs should satisfy is linear time temporal logic, which is basically an extension of propositional logic with a few operators that talk about temporal behavior of the programs. So we have the next operator that says that something holds at the next step in time, the until operator that says that some property will hold in the future, and in the meantime some other property will hold. And with this operator you can also express always and eventually, etc. These are classic. And the first problem, more precisely, that we're interested in is the problem of reactive synthesis that was introduced by Pinelli and Rosner. And so what is it? You have a finite set of inputs, a finite set of outputs, and your system plays, the system you want to synthesize is playing a game with the environment. And so how does this game go? First, the environment chooses an input, and the system has to choose an output in reaction to this input. Then the environment again chooses a new input, and the system has to choose a new output, and this goes on forever. And in the end, you obtain an infinite execution, and you want this execution to satisfy some property. So typically, the specification, the property that the behavior should satisfy will be expressed in LTL. And so given a specification, you want to synthesize a strategy for the system. So a strategy is a function that, given the finite history of inputs seen so far, tells the system which output to choose. So you want to synthesize such a strategy such that for all strategies of the environment, the resulting execution, when the environment and the system follow these strategies, satisfy the specification. So if you want to write that as a mathematical expression, you could write there exists a strategy for the system such that for all strategy of the environment, phi holds. We'll see a bit later how we can write it precisely in strategy logic. Now we can think about many interesting variants of this old classical problem. For instance, you may want to consider non-deterministic systems or strategies that allow for several possible outputs given for a given sequence of inputs. So in that case, a strategy would map histories, sequences of inputs, to a finite set of outputs that the system allows instead of just one output. And why would we want to do that? For instance, we may want to leave the possibility for different behaviors to occur in the system. If I write this formula, which reads as there exists a strategy for the system which is non-deterministic, such that for all strategies of the environment, there exists an execution in which P is always true, and there also exists an execution in which eventually I see not P. We see that if we consider only deterministic strategies, as before, this cannot be true, because given a deterministic strategy for the system and a deterministic strategy for the environment, you have fixed one execution which cannot satisfy both always P and finally not P. But if you allow for non-deterministic strategies, you have like more permissive system that can allow for different behaviors that may be both desirable, and you may want both to be possible in a system. But maybe you want that your system is able to choose which of these behaviors is executed. Maybe you don't want the environment to choose whether it will be always P or finally not P. So you may want to say more than the previous formula and say that in addition, so first these two behaviors exist, and in addition, the system can choose which one to enforce. Then you can also, you may also want to say that your system is permissive and allows to and satisfy some property, but you may want it to be as permissive as possible, maximally permissive. You may also want to talk about strategies that refine other strategies, so that first you have a strategy that satisfies some goal, and then you want a new strategy that keeps satisfying the first specification, but now in addition allows you to pursue another additional objective. And these are all properties that we will be able to express in the extension of strategy logic that I will present now. So first, let me remind what are the models of strategy logic. So they are classic concurrent game structures, which look like this. You have a set of states, which represent configurations of the game or of the system. And you have transitions between these states, which are labeled with tuples of actions. Here we have 3 actions on each transition, because so in the first example, we had just the system and the environment, which are 2 players, but in general, you can have as many players as you want. Here we have 3 players interacting together, and 1 action for each player determines a transition between the states. Here we have 2 possible actions, black and white. And each state, in addition, is labeled with atomic propositions that mark basic facts about the world. Now, a bit more formally, what is a strategy? It's a function that maps a history to an action. And a history here is a finite sequence of states that represents the sequence of states that we have visited so far. And a non-deterministic strategy will be a function from histories to subsets of possible actions. And we will say that a strategy sigma refines another strategy sigma prime if sigma allows for less actions than sigma prime in the sense of inclusion. So for every history, the set of actions allowed by sigma is included in the set of actions allowed by sigma prime. And so the set of behaviors allowed by sigma is also included in the set of behaviors allowed by sigma prime. Now, let me briefly remind what is strategy logic. It is an extension of linear time temporal logic with operators that allow expressing properties about strategies of agents in multi-agent systems, in concurrent game structures. A first operator is a strategy quantifier. So this formula reads as: there exists a strategy sigma such that phi holds, and a binding operator that allows you to bind a strategy to a player or to an agent. And this reads as: whenever player A follows strategy sigma, phi holds. And now we will allow for non-deterministic strategies, unlike most previous definitions of strategy logic. And we will add 2 new operators. So our logic consists of strategy logic with non-deterministic strategies, with a refinement operator, where this formula reads as strategy sigma refines strategy sigma prime, and an operator to quantify over all possible behaviors or outcomes allowed by the strategies currently used. Now, what can we write in this logic? First, a few simple examples. We can write equality, because two strategies are equal if one refines the other and vice versa. And we can write also that they're different. We can write that a strategy strictly refines another if it refines it and is different from it. And we can also specify that a strategy is deterministic. A strategy is deterministic if any strategy that refines it is also refined by the strategy sigma. And now we can introduce quantifiers over deterministic strategies by simply writing there exists a strategy that is deterministic and that satisfies the formula. Or for all strategies that are deterministic, I want phi to be true. And now let's go back to the examples of problems that I mentioned before. So first, classic LTL synthesis will be written with this formula, where we want a deterministic strategy for the system such that, so here I quantify on the strategy and here I bind it to the system, such that for all strategies, sigma prime deterministic strategies of the environment, psi is true in all outcomes, in all behaviors. Now, non-deterministic LTL synthesis. So we have said before that when both strategies are deterministic, this specification is always false because these two strategies determine a unique behavior that cannot satisfy both properties. But if we allow for non-deterministic strategies of the system and the environment, then this specification becomes satisfiable. Then I also mentioned that maybe we want the system to be able to enforce one or the other of these two behaviors. And this we can write to in our extension of strategy logic by saying that there must exist a deterministic strategy for the system that refines a given strategy. So one that satisfies this specification, and such that the formula you want to enforce is true. And then we can rewrite this specification as follows. I want a strategy, non-deterministic for the system and a non-deterministic strategy for the environment, such that the system can force always P, refining sigma, and it can also force finally not P by refining its strategy sigma. And briefly, maximally permissive strategies can also be expressed by this formula, which says that a formula is maximally, a strategy sigma is maximally permissive for phi if it allows for phi to be true, and for any other strategy that is strictly more permissive, then phi is not true. And so we can reason about synthesis of maximally permissive strategies. I don't think I have much more time to talk about these examples, but I just mentioned that we can also express module checking, which is another classic problem, refinement of Nash equilibria in multi-agent settings, etc., etc. And the main result, technical result of this work is that the model checking problem for strategy logic with refinement is not harder than for basic strategy logic. So model checking strategy logic is a problem that is quite hard, and it's k+1 x time complete for formulas of simulation depth k. So simulation depth, I don't have time to define it, but it's a refinement of the notion of alternation depth. So basically it counts how many times you alternate between existential and universal quantifiers and strategies in your formula. And so model checking strategy logic is hard, but it's not harder to model check the extension that allows to talk about all these notions that are not expressible in basic strategy logic. So to sum up, we have extended SL with these non-deterministic strategies and a refinement operator. And this allows us to allow many interesting problems without making model checking harder. Thank you.